Hello students, today we are going to study about the types of water, hydrogen peroxide and heavy water. Okay, now let us start with the types of water. Okay, water is of two types. Okay, hard water and soft water. Now what is this hard water and what is this soft water? Okay, when we use soap, okay, in water and it does not give leather means jar, okay, it does not give leather, okay, then that is a hard water. So what is the reason behind it that it is not giving the leather? Actually it is consisting of hydrogen carbonates, chlorides and sulfates of calcium or magnesium, okay. And here we are seeing what in this, the soap is reacting with this, what, the calcium and the magnesium hydrogen carbonate, chloride or sulfate, okay, and it forms a dirty precipitate and that is known as scum, okay. So here we are seeing what in this is the typical structure of a soap, okay, Na, single bond C, double bond O and a long hydrocarbon chain, okay. So what happens if it is calcium chloride, this calcium gets attached to this C, double bond O, single bond O, okay, COO. It gets attached to it forming what? Scum, okay, and here this Na precipitates out by combining with the chlorine present with the calcium, and naturally this sodium chloride is formed, okay. And so when this calcium is attached to this C double bond OO, it means COO, and with the long hydrocarbon chain, it forms what? A dirty precipitate known as scum, okay. Now here if we talk about this soft water, soft water gives leather with the soap, okay, because it doesn't consist of these bicarbonates, chlorides or sulfates of calcium or magnesium, okay. Now when we talk about this hard water is of two types, temporary hardness and permanent hardness of water. Actually this temporary hardness, when we talk, it is because of the bicarbonates of calcium and magnesium present in this water, okay. So we can remove this, the name itself suggests it is temporary hardness, okay. It can be removed by simple boiling process. What happens when we boil magnesium hydrogen carbonate or calcium hydrogen carbonate? When we boil it, magnesium hydrogen carbon, when we boil, it gives MgOH whole twice, that is magnesium hydroxide plus water plus carbon dioxide, okay. So what happens to this magnesium hydroxide? This is insoluble in water. As the result, it can be filtered out, okay, and this carbon dioxide is released in the atmosphere. Here if we talk about calcium hydrogen carbonate, okay, when we boil it, it gives calcium hydroxide and water plus carbon dioxide. This calcium hydroxide is lime and it is insoluble, and as a result can be filtered out. Carbon dioxide escapes in the environment and we get now the soft water. This is how by boiling we can remove this hardness of the water consisting of the bicarbonates of calcium and magnesium, okay. Now second method by which we can remove this temporary hardness is by Clark's method, okay. In Clark's method actually we add calculated amount of lime, okay, to this bicarbonates of calcium and magnesium, okay. So what is this lime? Lime is calcium hydroxide. So here calcium bicarbonate reacts with calcium hydroxide to give a PPT or the precipitate, that is calcium carbonate and water. This precipitate can be filtered out and we get the soft water right now, okay, after that. So here in magnesium hydrogen carbonate, when it reacts with this calculated amount of lime, that is so calcium hydroxide, it gives calcium carbonate and magnesium hydroxide and water. This calcium carbonate and magnesium hydroxide, they both are insoluble. They are in the form of precipitate. Naturally it can be filtered and removed out and we get soft water, that is H2O, okay. So here but just one thing you should remember, that yes, when calcium hydrogen carbonate is treated with this lime CaOH whole twice, we get as PPT only calcium carbonate. But when magnesium hydrogen carbonate reacts with calcium hydroxide, it gives out calcium carbonate as well as magnesium hydroxide, which is insoluble and can be removed, and we can get the soft water. Okay, now coming to the permanent hardness of water. What is the cause of this permanent hardness? Actually, it is caused due to the chlorides and sulfates of calcium and magnesium. Okay, so this has to be removed in order to make the water soft. So what we use is, first is we can use washing soda. Okay, what is the formula of washing soda? It is Na2CO3.10H2O. It is sodium carbonate decahydrate. Okay, but for convenience it is written over here in the books also Na2CO3. Okay, so here what happens, this magnesium chloride which is present in the water making it hard, okay, it reacts with this sodium carbonate, okay, and thereby giving insoluble magnesium carbonate and making the water soft. Okay, now next process by which we can remove the permanent hardness is the Calgin's method. Okay, so what is this Calgin? This chemical formula of this Calgin is Na6P6O18. This is Calgin. Okay, so when we are seeing this Calgin, okay, we will be seeing that yes, it is partially, okay, dissociated into Na plus ions, okay, 2 Na plus ions plus Na4P6O18. Okay, now this Na4P6O18, it reacts with the magnesium present in the hard water, with the magnesium ions present in the hard water, okay, forming what? In this MgNA2P6O18, which is totally insoluble in nature and can be removed, and this Na, it combines with the chloride of this magnesium and forming NaCl, thereby totally making the water soft. Okay, now next method is the ion exchange method. Okay, this method, it is economically fit method. Why? Because this is a cheap process. Okay, actually here we are using zeolite or permuted. So what is this zeolite or permuted? It is represented by letter Z and its formula is Al2Si2O8.XH2O. The water molecules are not fixed. Okay, so here for this whole compound Al2Si2O8.XH2O, which is zeolite, okay, this can be written as Na2Z. Okay, so here Na2Z, here we are using this zeolite, okay, and it reacts with this calcium chloride which is causing hardness of the water, or magnesium chloride which is causing this permanent hardness, to give the corresponding what? If we are using CaCl2, it will be giving CaZ plus NaCl. Okay, now we are seeing that yes, what happens in this, the total zeolite is being used. Okay, and if it is being used, then the process will become less efficient, and one time it will come that it will totally get deteriorated, and we can't remove now the permanent hardness of water. So this Na2Z should be recovered back. For getting it back, what we can use is, we can use NaCl, okay, and when it combines with NaCl, naturally it again gives back to us what? Na2Z plus CaCl2, and this Na2Z can again be reused, okay, again be used in the reaction to make the water soft and remove the permanent hardness. Now next is the synthetic resin method, or organic ion exchange method. Okay, actually when we are talking about these processes, washing soda, Calgon, ion exchange, okay, I said to you ion exchange is a cheap process. Why? Because here mainly to get back the zeolite we are using what? NaCl. NaCl is a cheap substance, isn't it? It is not so costly. Okay, so here we have seen yes, it is okay, but in the synthetic resin method or organic ion exchange method, okay, apart from this the chloride, sulfates of calcium and magnesium, if any other elements which is causing hardness in the water can also be removed, and we can get demineralized water in case of synthetic resin method and organic ion exchange method. And now let us study this method in detail. So now let us study about the synthetic resin method in some more detail. Okay. So I said to you the synthetic resin method. Okay. Here other elements, if it is present also, rather than the chlorides or sulfates of calcium and magnesium, this can be also removed. Okay, and as the result we get total pure water like a distilled water. Okay, and so we can say that yes, totally this water is demineralized. Okay, so what is the process behind it? Okay, this synthetic resin method. Actually, two types participate in this, that is the cation exchange resins and anion exchange resins. Okay, when we are talking about the cation exchange resins, we can understand that here the cations, the positive ions are exchanged. Okay, so in this what we are doing, actually we are taking the hard water and we are adding what? A cationic exchanger. A cationic exchanger can be a long hydrocarbon group joined with the carboxylic group, that is COH, or the sulfonic group, that is SO3H. Okay, so here for example, if we have taken RCOH, R represents the long hydrocarbon chain and this carboxylic group. Okay, here this hard water, it is consisting of calcium chloride or sulfate or magnesium chloride or sulfate, taken here calcium chloride. Naturally what happens over here, we can see that this calcium gets attached to this RCOO group, and what happens over here, this is removed out as H plus ions, okay, and Cl minus ions. Okay, and here this can be used for the regeneration also, this H plus ions and Cl minus ions, when this gets exhausted, this RCOH gets exhausted. One time comes actually when it will be finished off. Okay, and at that time, okay, if we are adding what? HCl to it. Okay, even this HCl can also work over here. This regenerates again. What does it regenerate? It regenerates again this RCOH, okay, which can be used again to make the water soft. Okay, and yes, this calcium is removed out and this calcium chloride is also removed out. Okay, now coming to anion exchange resins, what happens in this actually? Here the anions, they are removed like the chlorides and the sulfates. Okay, here we have seen what? The cations, that is what? The calcium. Okay, but here you are going to see about the anions, the chlorides or the sulfates. Okay, so here we are taking what? Water plus anionic exchanger. Okay, and this is what you can see here. This is joined to an anion. Okay, here long hydrocarbon chain having what? OH group attached to it. Okay, because this is only will be participating in giving out what? The chlorides and sulfates present in the hard water of calcium and magnesium. So here chloride ion from the hard water, okay, and this chloride joins with this RNH plus H3Cl and this OH is given out. How can it be regenerated? Okay, when we use NaOH, okay, it can be regenerated again. You can see again it is forming what? RNH plus H3OH and Na and plus Cl is given out. This is how we can make the water soft by using synthetic resin method. Now let us study about hydrogen peroxide, that is H2O2. Okay, so when this hydrogen peroxide, how can we prepare it? Okay, the preparation of hydrogen peroxide in the lab. Okay, so lab method first we are studying. We are taking this here BaO2.8H2O. This is what? Barium oxide. Okay, plus sulfuric acid. Okay, this gives us barium sulfate plus hydrogen peroxide plus water. Okay, now here Next method of lab preparation is by the electrolysis of 50% of H2SO4, means 50% of H2SO4 means 50% water and 50% H2SO4. Okay, so this H2SO4, okay, it breaks up into 2H plus ions plus H2SO4 minus ions. Okay, so what happens over here, this at cathode, this 2H plus ion plus 2 electrons forms hydrogen gas. Okay, at anode what happens, this H2SO4, okay, it gives, what does it give? It gives a compound, combining together giving a compound per oxyosulfuric acid, okay, and taking up the electrons from here, okay, and adding up with water, it forms a much stable compound than per oxyosulfuric acid, that is H2SO5, which is per oxomonosulfuric acid. Okay, and this per oxomonosulfuric acid also again combines with water, okay, or reacts with water to form H2SO4, which is more stable than that, plus hydrogen peroxide is formed. Okay, so this is how we can prepare hydrogen peroxide by lab method. Now, industrial preparation of hydrogen peroxide. We are going to prepare hydrogen peroxide in large amount. Okay. So, in this, what happens actually? There is auto-oxidation of two alkyl thioethanols. Okay. In this, actually, what happens? 2-ethylene thioethanol. Okay. In the presence of oxygen and palladium acting as catalyst. Okay. It gives 2-ethylene thioethanol plus hydrogen peroxide. Okay. Now, when we talk about the physical properties, okay, this H2O2, this hydrogen peroxide is a thick syrupy liquid, okay, it has got pale blue color, okay, and when we want to just dissolve it in water, it is totally miscible in water, like you can see with the, in case of vinegar, okay. It can also be miscible in water to any extent, okay. Now, when we talk about its dipole moment, okay, here we can see the dipole moment of hydrogen peroxide is greater than that of water, okay, and it is soluble in water. We have studied this, that it can be dissolved in water at any extent, okay. Now coming to the chemical properties of H2O2, okay, it is hydrogen peroxide. It has got oxidizing nature also and reducing nature also, whether the medium is acidic or whether the medium is basic. In acidic medium also it has got oxidizing and reducing nature. Basic medium also it has got the reducing nature in case of basic and acidic medium also. So both the characters we can see the oxidizing nature and reducing nature in case of acidic medium as well as basic medium. You can see the examples written over here or the reactions, okay, like in oxidizing nature when it shows what happens, it reacts with lead sulfide to form what? Lead sulfate plus water. Likewise it is reacting with Mn2 plus, okay, in basic medium, okay, here also it is acting as what? Oxidizing nature to form the corresponding compounds, okay. Likewise it is reacting with manganese oxide also in basic medium, acting as a reducing nature, okay, forming the corresponding compounds MnO2, that is manganese dioxide plus oxygen plus water plus OH minus ions, okay. Now if we compare this hydrogen peroxide with water, okay, it is slightly acidic than water. Okay, water is, when we compare it, water is a weak acid than H2O2. Okay. Now this H2O2 has got, hydrogen peroxide has got bleaching action. How it has got bleaching action? Why it has got bleaching action? Because it has one nascent oxygen. Okay. This H2O2, okay, we are seeing that yes, water plus this oxygen, this atomic oxygen, this nascent oxygen, okay, this is responsible for the bleaching action of H2O2, okay. It also shows addition reaction, okay. It adds up with this ethene, you can see, and it forms what? Glycol, okay. Now talking about the structure of this H2O2, okay, it is a non-planar structure. You can see that yes, it has got an open book like structure. This H2O2 at normal condition, it is not stable. Why it is not stable? Actually this H2O2, okay, in this normal condition it breaks up into what? H2O plus O2, okay. So here just balance the reaction, okay. So now here it is unstable, okay, breaks up into what? H2O plus O2. So we need to store this H2O2. In light, the reaction will take place and it will be decomposed to water and oxygen. Okay, so here we need to store it. We store it in dark, okay, in containers, okay, which are made up of plastic, or take a glass container and just line it up with wax, okay, and then this can be stored in that. And we can also use a stabilizer like urea to store this H2O2. So students, hope you might have understood this, the water, types of water and hydrogen peroxide. This is all for today. Good day. Take care.